Good day. I'm Mike and I'll be your tour guide through Calculus 2. Before we really start into Calculus 2, it's important to have some understanding of what we did in Calculus 1. So near the beginning of Calculus 1, you would have had some idea of a definition of a limit. Probably went into a precise definition of a limit, monotone limits. This is from either side of any point or as you go up to infinity and down to infinity. So you should recall some notion of this, as well as all these other things which I'll go through. Well, as you would have experienced, it's rather difficult to use the definition of the limit to calculate every single limit. And so the way around this is the limit laws and the divergent laws. So you probably would recall linearity limit laws, that the limit, a linear combination is the linear combination of limits, and the limit of a product is the product of limits. So you should recall some of these limit laws and be able to calculate simple limits using these limit laws, as well as other algebraic methods, including conjugate methods. Building upon the limits, you would have learned something about continuity. So continuity basically says that the value of a function at a point is equal to the limit as you approach that point, and the limit is defined as the limit both from the left and from the right. And so you should recall this notion and be able to test whether a function is continuous or not using limits. You also should have learnt the definition of a derivative in terms of limits. It's basically an increment of the function over the increment in x. And you should have learnt this and be able to calculate certain derivatives using the definition. But you should have then built on to be able to do more derivatives into the derivative rules. And the derivative rules largely follow from these limit laws plus the definition of the derivative. And so there's a linearity, a product rule, etc. as you've learned. You also would have learned things like the chain rule, etc. We should also have increased our knowledge of functions, so we should have some notion of what a polynomial is. Rational, which is a ratio of polynomials, so you should have had some exposure to those types of functions. Power functions, so that would be like x to the 1/2, which would be a square root, which would be a very simple power function. Trigonometric functions, sine, cosine, tangent, etc. Logarithmic functions and exponential functions. So in this Calculus 2, we're following on Calculus 1, which was largely an early transcendental approach, and so you would have had exposure to these functions. Also composite functions, which are just basically a function applied to a function. We should also have some knowledge about how to determine the domain, the range of functions, as well as their derivatives. And we probably built upon this to come up with higher order derivatives. So if you differentiate a function and you look at that derivative at all points, then it creates a new function, which you can often differentiate again, creating a second derivative, and you can repeat this process to create like an nth derivative. We also would have learnt the important notions of the intermediate and mean value theorems, which basically allow us to apply and to do a lot of graphing techniques and create a lot of knowledge about a particular function. And so we should not only know these theorems, but also how to apply them to obtain things like the regions of increase and decrease for a function, the regions of concavity up and concavity down, as well as the first and second derivative tests to be able to determine and classify the critical points of a function as being minima, maximum, or saddle points. We also should have learnt the definition of the Riemann, or equivalently the definite integral, from limits and Riemann sums, so we should have some notion of what Riemann sums are. We'll get back into this in Calculus 2 when we look at numeric integration. We also should have the notion of the definition of the indefinite integral, which at first look seems very different than the definite integral. The indefinite integral is the class of antiderivatives on the largest possible domain. You'll recall that when we did these indefinite integrals, we always added this plus c. This was to signify that actually it's not a single object that we're looking at, it's a whole class, and this class, by the mean value theorem, can only differ from a constant. We also, getting into the last parts of your first course, we would have looked at the integration technique of substitution, and this is a technique where we can use to calculate more complicated integrals from simpler integrals by breaking them down in this way. And the substitution is kind of like an inverse of the chain rule. And using this, we should be able to calculate indefinite integrals for some simple functions using this substitution as well as known formulas. Since indefinite integrals are classes of antiderivatives, so if you recall the function that you differentiated to get a different function, then going in the reverse direction creates a known formula for an indefinite integral. And then finally, you should know about the fundamental theorem of calculus, both parts 1 and 2, that basically say integration undoes differentiation and differentiation undoes integration in a more precise way. As well, we should be able to use these fundamental theorems to calculate certain types of derivatives as well as areas through definite integrals. However, I suggest to you that there's still a lot to learn. So let's start off by seeing what we know. So I'll start off and I'll ask you certain questions. So the first off, to see what we know, can you describe this Archimedean spiral mathematically?
It looks to me that it's almost like a circle, but the radius keeps getting larger and larger as we go in this fashion, rotate around in a counterclockwise fashion. One could describe that the radius gets larger.
But could you write down certain equations? So let me just elaborate on this. So first of all, we could ask ourselves, is this even a function? And the answer to that is easily determined. So if we drew a vertical line, then it doesn't pass a vertical line test, because depending where we drew it, maybe it passes this twice. If the spiral kept going, it would pass through it more than once. Or else, if we drew it over here, then it would be 3 times. If we were to draw a horizontal line, then the same thing occurs. So this clearly is not a function. However, you're correct in the sense that somehow or another you can see that this is sort of related to a circle with an increasing radius. So rather than explain and solve this now, we'll let this go, but we'll come back to it during this course. Let's move on to something else. How about this important limit? So this is the limit as h goes to infinity of 1 plus 1 over h all to the h. So can you solve this limit?
Well, I first see that inside the brackets we have a 1 plus 1 over h, and that I know goes to 1, since 1 over h will go to 0 as h approaches infinity. But then we have this h in the exponent, and I'm not sure how to deal with that.
What you can see is you could classify, and what we do is we look and we think, okay, well, what about this piece? Well, this is going to 1, so h is going to infinity, so this is kind of like going to 1. But then this other piece, as h goes to infinity, this is going to infinity. So what we have is we have type 1 to the infinity. We have a race going on. So the power of anything of anything positive to the infinity would go to infinity. But this is going to 1. And 1 to any power is 1. So you have competing things going on. You have an indeterminate form or race happening. So this base here is going to 1 and the exponent is going to infinity. And it's not clear exactly what happens. We're going to have to use some types of continuity and indeterminate limits to look at this. And again, I don't really want to solve anything here. I just want to motivate. So now you say you're an expert at differentiation. How about differentiating this? The derivative of x to the x. Yes, that's x to the power of x. X to be positive here, so everything is well defined. But how can you interpret this, and how would you do this derivative?
Well, I recall even from taking derivatives of x to the power of something, you use the power rule, but usually it meant that it was a constant and you just subtract it. For example, x squared would be 2x. But this seems different somehow because there's x to the power of x. My first guess would be we try to manipulate this somehow. I know that if I had something like a ln in there, then I can bring down that x. Maybe we could use something like e to the power of ln of the x to the power of x.
Right, so the suggestion is along these lines. So we could take this derivative and we could rewrite this, that this is equal to the derivative d by dx. And then what you could do is you could say exp, which is the exponential. And then what you could do is you could take the ln. So exponential and ln, we'll see that these are inverse operations, so this doesn't change anything. So we could write this as a derivative of the exponential of the ln. These two would just cancel out, so this would just give us x to the x again. And then what's being suggested was, well, then what we could do is we could write this as the derivative of the exponential x ln x. And now we have some type of hope of solving this. And again, I don't want to solve it here, but we'll leave this as a surprise and motivation for where we're going. Let's move on to this next problem. This next problem, which is, how about find this indefinite integral? So first off, how do we know that this is an indefinite integral and not a definite one? And second of all, how do you evaluate this? And what sort of result are you looking for?
I think that this would be an indefinite integral because you don't have the lower and upper limits. Usually you have kind of like the a and b on the bottom and the top of this symbol here, but I don't see that. So I do remember is equal to 1 over x plus c.
Actually, this is incorrect. So you've mistaken the integral for the derivative. The derivative of ln x is 1 over x, but the integral of ln x is something else. It will turn out to be x ln x minus x plus c. Another thing that you might have done is you might have thought, well, let's use substitution on this. So you might have thought, well, maybe we could use substitution on this because this is the only integration technique that we know. But sadly, that would just convert this to another integral that we also don't know. So you could, for example, use substitution to convert this to the integral of t e to the t dt. You could do something like that, but this is still an integral that we don't know. So we're going to actually have to use a new integration technique that we will learn called integration by parts to do this integral. So the next and final question I have for you is, what about this definite integral? So as you correctly pointed out in the previous question, so here we do have a lower limit and an upper limit. So we have an a and a b, which are -1 and 1 respectively. So this is definitely a definite integral, so we can think of this as an area. What's more is 1 over x squared, so since this is x squared, this is non-negative, so this could be interpreted as the area under a curve. So maybe you could explain on calculate and tell me what this one is.
What I would do is find the antiderivative for 1 over x squared, and 1 over x squared is the same as x to the minus 2, so the antiderivative would be minus x to the power of minus 1, and when I evaluate it from minus 1 to 1, that would give me minus 1 minus minus 1, which is minus 2.
Okay, so to understand this then, so if we took and we were to graph 1 over x squared, it would look something, it would explode up here, it would look something like this. Okay, it's always positive between minus 1 and 1, and it would blow up. And you're saying all this area under here actually is this negative number? So obviously there's mistakes here, and actually you've made a couple of mistakes. There's an algebraic mistake here somehow, so this should have wound up with a 0 if you had have done it that way. But the real point is that 1 over x squared, this is not continuous at 0. This means the definition of Riemann integral does not apply. But this is the more fundamental. So we have no idea how to handle this. In fact, if you look at this little picture here, this area may or may not be infinite, because this goes all the way up to infinity in this direction. So we don't even know at this point whether the value of this integral, we don't know how to interpret it, other than we'd like to interpret it as area under. But we don't know if it should be infinity or some finite number, and if it's some finite number, what on earth it is. In conclusion, from these 5 simple questions, is we still have a lot to cover in single variable calculus. So it's important that we have some understanding on various things, from limits, derivatives, integrals, even definition of integrals. We need to define something more to handle this last problem. There's still a lot more to cover. The first thing, so motivating on the spiral, the motivation of that, is we need to study curves, which is a mathematically fundamental notion, and parametric equations of motion. So we'd be able to describe this Archimedean spiral. We'd also be able to look and describe things like circles, ellipses, hyperbola, and more complicated motions in other and very useful manners. We also need to increase our functions that we know. So right now, as we mentioned, we know polynomial, rational, these types of functions, trig functions. But for integration, actually, we need to know inverse trigonometric, hyperbolic, and inverse hyperbolic functions. So these are really important functions, and they go beyond just defining these. They're going to help us do some calculations. We're going to define a new classes of functions. From the point of view of that limit that we had and we didn't know how to do it, which was a race, what we are going to learn more about is how to handle these indeterminate limits or races by transformation and use of L'Hopital's rule, as well as other methods. And you'll remember also that we had the derivative of x to the x, which we didn't really know how to handle either. And so we need to add new rules to be able to handle this and other examples. So, for example, once we have defined and know the derivatives of trigonometric functions, it would be nice if we knew then how to compute the derivatives of inverse trigonometric functions. And this will necessitate the so-called inverse function derivative rule. And to be able to handle things like the derivative of x to the x, We'll learn the POW-X rule, which is very related to the product rule, but it adds a lot of power. And with these rules, we'll be also able to increase dramatically the list of functions that we can differentiate. Exciting, right? We'll also, in the same process, so as we increase the list of functions that we can differentiate with known derivatives, just by looking at the same table in the reverse direction, we're increasing our list of known antiderivatives and indefinite integrals. So this is what's especially important for why it's especially important that we know how to calculate the derivatives of inverse trigonometric and inverse hyperbolic, because when we apply it in the reverse direction, it's going to be most useful to us. Also, to be able to calculate yet more integrals and to be able to handle things like the integral of ln or any logarithmic function, we need to learn the integration technique of integration by parts. To be able to integrate any rational function or functions that are transformable through substitution, etc., to rational functions, we're going to learn the integration technique of partial fractions. These are two very, very important integration techniques, just like substitution is. To be able to handle this last example that we had, which was the area under 1 over x squared, we have to define a new integral. So let me ask you, how many integrals do you know now?
I don't know. 1?
Actually, you know 2. Just think, how many definitions are there? Well, there's 2. There's the definition of definite or Riemann integral in terms of limits of Riemann sums. And there's also the definition of indefinite integral in terms of antiderivative. It's the class of antiderivatives over the largest possible domain. You know 2 integrals. We're going to learn a third one, which is in the improper integral. And we're going to learn how to compute them. But there are many, many more integrals. There's Lebesgue integrals, Stieltjes integrals, Ito integrals. There's all kinds of different types of integrals around. And in this course, we will just add to go from 2 to 3. We'll also learn how to apply these types of integration techniques to solve some simple yet important problems like arc length of a curve. For example, how long was that Archimedean spiral? So if we went around that spiral, say twice, how much string did we use if we stretched that out around the spiral? Also, we'd like to know area and volume. So what is it, simply, for example, very simply, what is the area of an ellipse? How could we derive it? And then finally in this course, we'll introduce the notion of differential equations, and we'll just look at very simple, linear, and separable ones. And I want to, because that was a lot, you probably got more than you bargained for in this introduction, I just want to stress the 3 most important concepts that we will really strive to drill home in this course, in this tour, are those notions of curves, integration techniques, and improper integrals. Improper integrals are important on their own right, but yet they're also important for concepts, for understanding things like series, which will come in a follow-on course. Thank you.